Welcome to the Small Unmanned Aircraft System for Agriculture Risk and Reward webinar series. This webinar series is supported by 4 faculty, starting with Dr. Mang Mangu at Texas A&M AgriLife, Rusty Ramley, Staff Attorney at the National Agricultural Law Center, Dr. Jomari Maha, Remote Sensor Engineer at Clemson University, and Dr. Jim Robbins with the University of Arkansas System Divisions of Agriculture. The purpose of this session is to provide an overview of the workflow, software, and image processing related to using a Small Unmanned Aircraft System, or SUAS. This session is part 6 of a 7-part series. These webinars are partially supported by a grant from the Southern Extension Risk Management Education Center. No endorsement is implied or discrimination intended for firms or references included or excluded from these presentations. We also would like to recognize the support from McCorkle Nursery and J. Frank Smith Family Foundations. This webinar is for educational purposes only and not meant to provide legal or regulatory advice for the safe and legal operations of any small unmanned aircraft system. It is the responsibility of the SUAS user or pilot to read, understand, and follow all FAA regulations. Again, simply to mention that this is one webinar of the content of the 7 webinar modules that are included in this series. The webinar team has developed several handouts that are available at the URL on your screen, or contact one of their presenters directly. Remember that there are lots of issues to discuss when dealing with SUAS, and this is part 6 of the 7 webinar modules. This webinar will focus on workflow, types of software, and examples of image processing. Let's get started. These are the list of softwares that I'm going to demonstrate to you today, and most of these softwares are open source. QGIS, previously known as Quantum GIS, is a free and open source cross-platform desktop geographic information system application that supports viewing, editing, and analysis of geospatial data. We're going to use this software to provide quick computations of our NIR image or near-infrared into something that we can use to evaluate plants' health using NDVI, or Normalized Difference Vegetation Index. The second software is Microsoft EYES, or Image Composite Editor. Microsoft EYES is an advanced panoramic image stitcher, or stitching software, created by the Microsoft Research Computational Photography Group. I'm going to show on how to use this software to stitch multiple images that we collected using our drone on one of the nurseries that we visited. ImageJ is a Java-based image processing program developed at the National Institute of Health and the Laboratory for Optical and Computational Instrumentations, or LOCI, at the University of Wisconsin. I'm going to use ImageJ to process a single image by extracting the near-infrared band and the red band, and use the extracted data to generate the NDVI. Again, NDVI, as mentioned on the previous module of this webinar series, mentioned that it's an indice that we can use to evaluate the health of the plant. MeshLab is a software used for processing and editing 3D triangular meshes. It provides a set of tools for editing, cleaning, healing, inspecting, rendering, texturing, and converting meshes. Though with the advanced functionalities inherent in this software, I am going to use this to demonstrate on viewing 3D images generated from one of the stitching softwares. And lastly, Agisoft Photoscan. The Agisoft Photoscan is a standalone software product that performs photogrammetric processing of digital images and generates 3D spatial data to be used in GIS applications. The software can also be used for some other things like cultural heritage documentations and visual effects productions, as well as for indirect measurements of objects of various scales. Before we proceed with the software demonstrations, I would like to refer you to this workflow that I have been using whenever we are collecting aerial images. Again, this is for educational purposes only, and you're welcome to use this workflow as a template on your aerial data collections. I'll show you all the workflow first before we go to using all the softwares I mentioned on the previous slide. Based on this workflow, I always start with NOTAM filing or Notice to Airmen applications. I use this URL to file my NOTAM. Though it isn't required for SUAS pilot with Part 107 license, I think it is a good practice to still file a NOTAM to help other SUAS operator know that you are flying on some location that they might have plans to fly as well. This is the website where you can file your NOTAM, 1-800-WXBrief.com. You need to register first before you can use this service. On top of the website, you will find 9 tabs, and under the UAS tabs is where you will file your NOTAM. These are the following information that you need to file the NOTAM. First is the aircraft registration, the address or locations of the flight, the date and time of the flight, the altitude, the frequency of flight, meaning if you only need to do one flight or recurring, and lastly, your contact information. Also, under the UAS tab, you will find a sub-menu named UAS Operating Area. If you click on this sub-menu, it will display the continental US UAS map of the current and recurring NOTAM only for small unmanned aircraft system. So after the filing of Notice to Airmen, the second workflow is the setting of waypoint navigations. Depending on the software of your SUAS, you can plan your flight path ahead of time using either waypoint navigations, 3D map generations, or PhotoMap. The software on this slide is from DJI GS Pro. Though we can create our flight plan easily on the field, I highly recommend that you do this ahead of your flight to make it easier when you are already on the field. The information that you need to create the plan are map of the flight area, the altitude, the area coverage, and depending on your objective, the percentage of overlaps. There are 3 different types of triggers that you can use to collect images. One using an intervalometer. Second is manual trigger. And the last one is using distance trigger. Intervalometer is either another device or built in from the camera sensors, which control how often shots are triggered. Most of the time, the frequency of shots can be programmed in an interval of 1 second, 3 seconds, or as long as 1 shot per minute. Intervalometer is often used so SUAS pilot or operator can focus on the flying. Manual trigger is also another way of collecting data. This is normally used when one only needs to collect a single shot of a small area. Distance trigger is a special trigger mechanism that is part of the SUAS software. The SUAS will trigger the sensor camera at fixed distance, and the distance is calculated based on the height, altitude, the area which you want to cover, and the overlap. After the flight, you can download the images to your computer, and before you can process your image, we suggest you just need to do a quick assessment on checking the images and discard images which are blurry. This will decrease the time to process the image that you collected. Here is an example of a stitching software. This is the Agasov Photoscan. The software will try to approximate the distance and location of your images, not based on the map but based on the local area. Unless, of course, if your image is georeferenced or has a GPS information. Then the software can produce a KMC file which you can use in Google Maps. Stitching using Agasov Photoscan takes multiple steps, but the good news is that you can create sort of a batch file that you can save and reuse it to process the images. The batch file will mostly work most of the time as long as the images were clear. Again, if you don't have a georeference image, you can use other software to georeference the image to a map and produce a georeference images as an output. You can easily do this using QGIS. Here are some results of using different stitching softwares or services. We use the same set of images to compare the results of Microsoft Eyes, which is free, and Agasov Photoscan, which is a commercial software. On this example, Microsoft Eyes provides better results compared to Agasov. You will notice that the Agasov software have some difficulty on the edge of the irrigation hose and also on the lower edge of the image. You can notice that on the white area of the image. We also tried stitching using the service company named Drone Deploy, and we compared the results to Microsoft Eyes. Here's the stitch image result from Drone Deploy and Agasov Photoscan. This is an example on how to georeference an image using QGIS. QGIS is a neat function that you can use to georeference your SUAS stitch image using Google Maps as reference. The important part of processing the SUAS stitch or single image is to use the data for analysis. NDVI, or Normalized Difference Vegetation Index, is just one of the indices that one of our presenters mentioned on this webinar, but the most popular one. Before we can process this image, we need to isolate the channels or band on this image. This is a very good example of using ImageJ to split the channels. Once ImageJ split the channels, it will generate 3 different images, one for each band, red, green, and blue. Since we are using multispectral cameras or sensors, we need to make sure that we know where the near-infrared band is. This is normally indicated by the manufacturer of the multispectral camera. So depending on the manufacturer model, the near-infrared can be either on the red or blue channel. As what my previous colleague presented earlier, NDVI is calculated as near-infrared minus red divided by near-infrared plus red. Once we split the image into the 3 bands, we can use the image calculator of image J to calculate the NDVI. Note that the values of NDVI will range from -1 to 1. That means the result of the calculator will only show a gray level image or 1 band. The left image is the NDVI calculated image, and the 2 other images, which is a green colored, is actually the same image but only shows a green color for healthy or less stressed plant. Now this is the result of using a lookup table to generate a visual representations of NDVI. Green is healthy, and dark colored or light colored or red color is not good. So ImageJ is a very simple software that can be used to rapidly assess a small plant. Aside from georeferencing a stitched image, QGIS can also calculate the NDVI of stitched image using the same formula of NDVI. I am going to show later on how we're going to do this using raster calculator. And lastly, there are a lot of applications of generating a 3D data on certain farm. One can use it to measure the height or measure the canopy of the plants, and this has been extensively used in Spain. I will show you the 3D data that the Agusoft Photoscan generated, and I will use the MeshLab to display the 3D model and measure the height of the plant as shown on this slide. Again, just to give you a summary of the workflow, we start with NOTAM, waypoint navigations, image capture, download and enable weight images, stitching, 3D model, georeference, and lastly, the calculations of vegetation indices. In this case, we use NDVI. So this is the ImageJ demonstration. So this is just a shortcut of ImageJ. Try to run that. As you can see, you have this very small dashboard for ImageJ. So the first thing that you need to do is to drag and drop this near-infrared image to the dashboard. So we have this one. So this is our near-infrared image. So as what I've mentioned in the PowerPoint presentations, we need to first split the channels for this near-infrared image. To do that, we go to the image tab, and then you choose color, then click on split channel. So this is our blue, this is our green, this is our red. So for this multispectral camera, the blue channel is our near-infrared channel. So for us to make it easier, we'll just rename this channel to near-infrared. Okay, so right after that we go to image calculator. So we're going to use exactly the same NDVI equations, near-infrared minus red and divided by near-infrared plus red. So let's start first the numerator. So choose near-infrared, subtract to red, and we have to click create new window. That means after the calculations it will create a separate image, and also we need to click also the 32-bit float result. Okay, so this is our near infrared minus red. Let's rename that one as our numerator. Okay, now going back to the process tab, still use the image calculator. So our image 1 is near infrared, but this time it's add plus red, create new window, 32-bit float result. This is the result of that calculations. We're going to rename this as our denominator. Okay, so now we're ready to calculate our NDVIs. So the same thing, we go to process, choose image calculator. So now we have to use numerator divided by denominator. Same thing, create new window, 32-bit float. Click OK. So this last window here is our NDVI. Okay, so I'm going to hover my mouse on this image here. As you can see on the bottom part of the dashboard of image J, you'll see the calculated results. So here it's negative 0.35. If you go to the plants, you get smaller values, or higher values compared to the one on the black tarp. Now we can minimize all this. We can also use, as what I mentioned, the lookup table, just to represent. Darker green means higher NDVI calculations, and a lighter green would mean a lower NDVI. So this is a lookup table that I created. You can create your own lookup table, but this is just, it does not actually change the values of NDVI, but it just shows it just changes the how you look at the image. So to use this is you just basically drag and drop this to the dashboard. Okay, so this is the reverse NDVI. So for you to create the correct NDVI calculations, you have to invert the loop. So this is what comes up here. So this is actually how you do a NDVI calculations with one image using image J, which is very, very quick. Okay. Okay, so this is for demonstrations on how to stitch multiple images using Microsoft Image Composite Editor. So I already click the this is the ICE software, and I'm going to use these different images that we collected in North Carolina. So actually this sample image was actually used on our PowerPoint slide. So there's about 44 images that we collected in here. So what we need to do, since I already check each of these images for blurry image based on our workflow, we need to make sure that there's no bad image on this group of images, so it will be easier for our stitching software to process all of them. So let's press Ctrl A and then just drag and drop that to the image composite editor and click next. So as you can see, what it does is it tries to align the images, and then once it's done aligning the images, it will try to group them together. That's what they said, compositing images. But this is very quick. If you are going to stitch this image using Agisoft Photoscan, it will probably takes a little over an hour. But for ice, it will be, let's see, will be probably less than 5 minutes. Okay, so now it's done aligning. It's going to put them all together. And what's good with ice also is you can, once it's done stitching, you can rotate the resulting image to whatever you want, or you can even crop it as well. I'm going to show it to you later, because sometimes when you are stitching multiple images, the side of this stitch image is kind of not straight, but yeah, you can actually edit that directly through ice software. There you go. So this is the stitch image here. We can, as I mentioned earlier, we can rotate this. Let's say we rotate it 10 degrees to the left, or if you want to rotate it, put it back to 0. Let's just rotate it a little bit, maybe 3. Okay. So then you just click next. And now here we're presented with this screen where we can actually crop the resulting stitch image. So if we click next, it's going to crop the image, and this is the stitch image as well. So now we're done. We actually need to export the result or webinar. Let me type the stitch image. The output is, and it's done. So yeah, less than 5 minutes, and this is the result here. There you go. You can zoom in, and that's the result of the Microsoft Image Composite Editor. Thank you. Okay, so this is the demonstrations of how to georeference a stitch image. So we're using actually QGIS here. The versions of our QGIS is, oops, sorry about that. Version is 2.18.15. So this is not the new version. There's a new version now that's being released by QGIS, but this is the software that we use for our demonstrations. So the first thing that you need to do is to open a new project, and then we'll try to load a map using Google Maps. So you go to Web, open Layers, and then let's just use a Google satellite map. So for you to upload the map, first thing is we need to define our coordinate system. So we'll use the WGS84 or EPSG4326. Click apply. Don't worry about the errors here. So then we need to plug in the latitude longitude at this coordinate bar underneath. So I already prepared my GPS coordinate. So what I'm going to do is I'm just going to copy this and put this in that bar. So this is just to show you that this is the near-infrared image that we're going to georeference. This is the near-infrared image from one of our plot at the Edisto Research and Education Center. So now I'm going to copy this GPS information down. Press enter. Then I'm going to change the scale. Okay. So if we're going to open our near-infrared image, you can see that there's some similarity here on the Google Maps. Unfortunately, this image doesn't have a GPS information. That's why we need to georeference the image. So first thing that we need to do is to go to raster, and then under raster you go to georeferencer. And in here we need to load our stitch image. Then we have to make sure that the coordinate reference systems that we use must be the same with the one that we use on our QGIS. That's WGS84, EPSG4326. So what we're trying to do here is we're trying to find a point that we find from this stitch image to what we can see from the Google Maps. So normally I have a minimum of 4, but the more the better. So first thing is we need to make sure that our transformation settings is correct. We have to use a transformation type thin plate spline. Our resampling method should be nearest neighbor. And again, we have to make sure that our coordinate reference system is the same. And then here, it's the most important thing, because this is, once it's being georeferenced, it saves to another file, which is a TIFF file. So we need to just define a new file. We'll just define this as georeference file. Use 0 for transparency when needed. That means that, if it doesn't see that on the map, it just makes it 0. No compression. And I think you need to click on load in QGIS when done. That means after it georeference, it will actually automatically place it on our QGIS map. Let's click OK. Then the next thing that we need to do is to add a point. So it doesn't need to be very precise. I think you can play around with this one as you learn on how to do it. So the first thing, let's start with adding point. So let's say I'm going to use this point here and this point on the Google Map. So if you click on that point, just click from Map Canvas, and I'll click OK. That means I accepted that point. it will record that point underneath here, the table. Now let's find another point, this one here. Then click from up canvas and click OK. So that's our second point, as you can see down here. And let me go here, click from up canvas and click OK. And lastly, let me use this part here, from up canvas, click OK. So we have 1, 2, 3, 4 already, and you can see actually the points that we click on Google Map as well. So that's 1, 2, 3, and 4. So when you're ready, you just click this button here. It says Start Georeferencing. So here it shows that the raster was successfully created. And if you try to move this one a little bit out, you see that your image, stitch image, is now uploaded to our QGIS. Now we can save this point. We call that as our ground control points. Rep GCP. Save. Then we can close this one. Okay. So now we're here. So this is actually superimposed to Google Map. And this file here is actually the georeference image already. So the second part is we're going to calculate the NDVI of this georeference image. So as what I mentioned, QGIS has a raster calculator. So we go to raster and raster calculator. And here we know that our band 4 is our near infrared, and band 2 is our red. So we can also save our computed NDVI to another file. Let's call this as computed NDVI. And you remember that the calculations of NDVI is near infrared minus red divided by near infrared plus red. So we'll do that. Near infrared minus red divided by near infrared plus red. Close. And then click OK. Here. So this is the computed NDVI, and notice that the computed NDVI image is one band. That's what I was saying before, that it's a gray level image. And here underneath, under the coordinate system, as you can see, this is the longitude latitude. If I'm going to hover my mouse on top of this image, it's going to change as well. Here on the left side, you can see that there's another file created, another layer. This is our computed NDVI. And these are the values, the maximum and the minimum. Now notice that in most of this NDVI that you've seen in the internet, that it's a mixture of different colors. It's basically just a representations of different numbers or range of computed value. And the good thing is we can do the same thing here in QGIS. So and how to do that is you double click the computed NDVI layer, and then these layer properties will come up. Under render type, let's change that to single band pseudo colors. So there's a lot of, this is what we call the lookup table as well. So you can choose different kinds of lookup table that you use, that is available with QGIS. We're going to use the red, yellow, and green. Red means bad, and green means better. So once you choose that one, you just click classify, and it will come up with all of these ranges. Then once you click apply, it's going to add these colors to your calculated NDVI. So now if you hover your mouse on the red, you can see that the numbers of calculated NDVI is smaller. Okay, so if you're going into the green, you have an NDVI of 0.349 here, but if I hover my mouse on the red or on the road, the NDVI calculations is 0.26. So that's how easy it is to georeference an image, to compute your NDVI in QGIS. Okay, so we're here going to demonstrate the MeshLab demonstrations. Now I already have this file that was actually being generated by Agisoft Photoscan. This is the file PLY, and once you have that, you can actually go to MeshLab, and here's the MeshLab, and you can upload it to MeshLab. Since I saved this one already, so I just need to double click on that file, and this is what MeshLab is. So you can I mean, this doesn't have any meaning because this is just a two-dimensional, but once you go here and then move this on the side, you can see that now it's a 3D. So, well, it looks good, but I think the most important part of this 3D MeshLab is you can actually measure the height of the pot. So you go to Edit, click Measuring Tool, then just define that this is our ground, then click. There you go. So you have this value here. You can see it, 0.481925. But this calculations is unitless. So what you need to do is to correlate these numbers to real world measurements. So if you have that real world measurements, then you go ahead and you can measure all the height of these plants here in this 3D mesh. Okay, so that's it. I think. Thank you very much. This concludes part 6 of a 7-part series. We hope this series helps reduce your risks in dealing with SUAS or drones for agricultural applications. Thank you.